This is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. In today's topic, we will see the problem solving on introduction, which is module 1. So here we can see the question like build a mathematical formulation for inviscid incompressible irrotational flow by reducing inviscid incompressible irrotational flow by reducing the governing equations of fluid flow. Okay, so here what do we have? So basically the inviscid, so the meaning of inviscid is so the viscous force, so the mu, like we will take it as negligible actually. So we will actually, the viscosity is also negligible. So basically this is dynamic viscosity. So where we say that the viscous forces are negligible, or let's say we'll consider that mu term as 0. So that is the meaning of inviscid actually. So incompressible. So the meaning of incompressible is density rho as constant. So with respect to space or time. So rho is function of x, comma y, comma z, comma t. So x, y, z. So the space coordinates and the time. So if it is steady, so then it is constant with respect to this. When it is unsteady, so this term will be there. So what is that? X, comma y, comma z, comma, so time. Fine. So density is function of time. Now, so what do we have? So if the flow is incompressible, so this density x comma y comma z is equal to constant. Fine. So constant in the sense it will not at all vary actually. So we vary with respect to the space coordinate. So let us draw a 3D diagram. So where this origin of x, y and z. So here you have a fluid particle. This is going from here to here. So what happens actually? So here the density, let's say this is rho 1, which is rho 1, which is function of x1 comma y1 comma z1 comma t1. So this is this one. So here it is function of rho 2, which is x2 comma y2 comma z2 comma t2. Fine. So this is what we have. So one is rho 1, one is rho 2. So where if rho 1 is equal to rho 2, then the meaning is incompressible. Fine. So the density of the particular fluid particle will not vary, so with respect to time or space. So the irrotation in the sense, so here if we consider a ball, so let us take this as ball and let us take this as boundary layer. So this boundary layer formation will happen when you have the viscosity. So when the viscosity term is not equal to 0, then you have this boundary layer. Now here what is happening? So let us take this as U2 and this one as U3. So we have a fluid particle here. So this is the center. So you have this velocity U3. So you have this velocity which is lower U2. So because of along y direction, you have change in velocity. So because of this change in velocity, which is du by dy, so we have the rotational effect of the fluid particle in this direction. So therefore, what is the meaning? So here, when you take a fluid particle, when you have the viscous effect, then you have the rotation of the fluid particle. So if the same fluid particle, let us take this one. So here you have u3, again here you have u3. So the velocity u3, if it is same, then what happens? So du by dy term is equivalent to 0. So it will not vary. So therefore what happens? So this is the condition of mu equal to 0. So therefore what is the meaning? So if the flow is inviscid, ultimately so it will have the rotational effect. Fine. So if the flow is viscous, so you have the rotational effect of the fluid particle. So the rotational effects of the fluid particle is coming because of the change in the velocity from one layer of the fluid to the other layer of the fluid. So that is why. So you have a rotational effect. Right. Now we have to deduce the expression, governing equation of the fluid flow to build this inviscid incompressible irrotational expression. So let us take the generalized equation, so which is dou rho by dou t plus del dot rho u equal to 0. So this is the generalized expression for the continuity. Now what we have seen from the incompressible, density is constant. So when you have the density constant, what happens? So this term will vanish, will be equal to 0. So the obtained expression is del dot rho u bar equal to 0. Then from this the density term comes outside. So where del dot rho u bar equal to 0. So this is expression applicable for incompressible flow. So the continuity equation will not give us the detailed information about the viscosity, whether the flow is inviscid or viscous or irrotational kind of thing. So it will be shown basically whether the flow is incompressible or compressible or not. Like here you can see clearly. Now, when we come to the other equation, which is momentum equation, let us take. So we have capital D. Sorry. So we have du by dt so is equal to 1 by rho minus dou p by dou x plus mu square dou u by dou x square plus square u by dou y square. So this is basic momentum equation. So for this basic momentum equation, so what do we have? So we have this one is called the substantial derivative or material derivative or total derivative. So let's see basic what is du by dt. So or let us see what is this d by dt. So d by dt is nothing but combination of dou by dou t plus v dot del. Okay, so this is the formulation for d by. So this is called total derivative. So this one is called local derivative. So this one is called convective derivative. So we have a total derivative or material derivative. We have local derivative. So this one is called the instantaneous or with respect to time how it changes. So let me draw a diagram. Here you get to know. So if you take this as origin, x-axis, y-axis, z-axis. So you take a fluid particle here, you take here, from here, here. So this is going, let's say in this way. So here, at each and every time, let's say this is T1, this is T2. So somewhere in between Ti you have intermediate time. So at each and every instant, with respect to this first term, so basically dou by dou t. So this term is called the instantaneous derivative, or let's say the derivative with respect to local time variation. So here you can see v dot delta. So this v dot delta is called convective derivative. So when this fluid particle is going from station 1 to 2, So with respect to space, it is moving. So when it is moving with respect to space, so what is the change in acceleration? So this is called the local acceleration. This is called convective acceleration. So the combination of the instantaneous or the local acceleration plus the convective acceleration will come to the total acceleration actually, or you can say total derivative is the combination of the local derivative or the convective derivative. So which is moving from station 1 to 2, let's say point 1 to 2, right? So this is what happens. Now here what is happening actually, so when it changes from one point to other point, now here the density value, so the flow variables which is density, velocity, and let's say u velocity, v velocity, w velocity, so temperature, so these are our primary flow variables which will govern the fluid flow. So these parameters actually will change with respect to this. Fine. Now, so when we have this expression dou by d by dt of u, so let's say you have small u, then what happens? So that will be dou u by dou t plus b dot del of u. So this is what we have. Fine. So here, if we substitute this expression in the previous equation, so this is what we are finding. So here you can see this is what we need to replace. So the dou u by du by dt, the total derivative or the material derivative or the substantial derivative is replaced now. Okay. So we take this as u. Now what happens? So du by dt which is equal to, so dou u by dou t plus v dot del of u which is equal to minus 1 by rho dou p by dou x plus mu square by rho, so which we have, or let's say this is mu by rho, which is dou square u by dou x square plus dou square u by dou y square plus, if you consider the body force term, rho of gx. So this is the generalized momentum equation. So this generalized momentum equation, what we are doing actually, so we are changing with this assumption, the implicit thing must happen. Incompressible already it is done. Why? Because if the flow is compressible, so the resultant this equation would have, so dou by rho of u by dou t plus v dot del rho u which is equal to minus dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square plus, actually here plus rho g x. So this is the equation, the bottom equation. This is applied for the full form of equation which is compressible, rotational and viscous actually. So the above equation what we have, so this is applied for the inviscid, incompressible, inviscid, when you have the inviscid, this term, the viscosity term will be 0. So if the flow is viscous, the viscosity terms will be there. So this equation, the above equation is applied for the incompressible. Now when we want to see the full form of equation, full form of equation in the sense we want full inviscid, incompressible, irrotational, then the equation changes to dou u by dou t plus v dot del of u is equal to minus 1 by rho dou p by dou x. So this is the equation, and the other equation we have del dot, let's say u equal to 0. So if we expand this one, that will become dou u by dou x plus dou v by dou y equal to 0. This is what we have. Fine. So here, how do we solve actually? Now we will have to discretize this equation. So if we apply the forward difference, so u of I plus 1 minus u of I divided by delta x plus, so in the case of 2d, you have to write j. So next v of I comma j plus 1 minus v of I comma j divided by delta y equal to 0. So this is one index notation form, or let's say this is what we call is like the linear form for the continuity equation. So here we write this one where you can see u of I to the power of n plus 1 minus u of I to the power of n. So I comma j, you can write I comma j divided by delta t minus, so here it will be u of I into, so here you will have u of I plus 1 comma j to the power of n minus u of I comma j to the power of n divided by delta x. Okay. Next, we have the other term which is plus u of I to the power of n into, so u of I comma j plus 1 to the power of n minus u of I comma j to the power of n divided by delta y, which is equal to minus 1 by rho of I comma j. Here it will be p of I plus 1 comma j minus p of I comma j divided by delta x. So this is the full discretized equation for this equation. Fine. So here discretized equation for this equation. So what we do, we write the discretized equation for each and every expression. So here you can see this is for inviscid, incompressible, irrotational, and flow, which is built by the governing equations. Now these equations, when we are solving, so the initial time level, so what happens at t is equal to 0, we need to predict the values. So at t is equal to 1, t is equal to 2, t is equal to 3, 4, 5, 6, so on, will be calculated as the simulation progresses. So the delta t time step is also a very important factor. You can see we have delta t and delta x. So in the previous modules or in the previous sessions, I've been keeping on telling like delta t and delta x. So they are going to play a major role. So where you have a formula called current number, which is u delta t by delta x. So this one will give the stability of a numerical scheme. So whether your numerical scheme is stable or unstable or partially or conditionally stable, so these things is discussed by this parameter, which is u delta t by delta x. Now this expression is built for the implicit like explicit scheme. So where as we discussed, the explicit scheme is nothing but the n plus 1. So here you can see there is only one flow variable. So where u of I comma j to the power of n plus 1 is the one unknown variable which we have. The other variables, which is u of I plus 1 to the power of n, so whatever the values power n we have, so those are the initial variables or the initial conditions or the initial variables. So wherever you have n plus 1, so those are called the variables which are to be estimated or to calculated at the next step, or the let's say the simulation step, or the consecutive time steps. So the n values, let's say it will go from 0, or like here we will consider from 1. So 1, 2, 3, so on till the time f t final actually. So till t final, you will keep on running the simulation. You will see you'll update the values by storing them in different grid points, or let's say different data sets, such that you will get the final step. Fine. So with this, we have seen one problematic case for the module one. So where we have discussed about the inviscid rotational incompressible flow, which is the expression built from the general governing equations. So where we have seen that the viscosity terms are negligible for the inviscid for irrotational, but whereas for the compressible incompressible flow, the density term both for the time derivative and both for the space derivative has to be neglected to consider the flow as incompressible. Therefore, for all incompressible inviscid irrotational flows, you have to take density constant and the viscosity constant. So with this, the flow parameter equation variables are getting reduced. So let's say if we have the density, pressure, u velocity, v velocity, w velocity as the five unknown variables. Now, when we consider the equation as incompressible, so then you have pressure, u velocity, v velocity, w velocity, four variables, and there you have four equations to solve very easily. Actually, when we does not consider in like, the flow as inviscid, like we have this four. When we consider flow as inviscid, the complexity will still come to lower level, where you will consider the like eddy viscosity as zero, like you don't have turbulence phenomena. You consider the flow as entirely laminar. Therefore, so whatever the expression we have built, that is very simple flow, which is applicable for the laminar cases, and where the viscosity does not change and the density does not change with respect to time and space. So in the next sessions, we will see the problematic solving cases for the other modules. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.